What's up, guys? Welcome back to the eCoreAcademy e-learning platform today. My name is AJay Raj, back with yet another geometry course video for you guys. And before we jump into today's lesson, please make sure to smash that subscribe button down below, hit that like button on this video, as well as hitting that post notification bell to get notified on any of our channel's latest posts at eCoreAcademy. It's very much appreciated. Alright, let's jump right into it. Today's lesson topic is all about geometric reasoning. And the purpose of this whole entire lesson is to discover the steps and components needed in order to develop proper reasoning for geometric relationships and concepts. This lesson in itself is actually a very important fundamental because as you get into later geometric concepts, such as discovering area, volume, angle postulates, all these complex and high-level concepts that you're going to get into later, and all these other geometric topics that you're going to get into later, it's all going to revolve around reasoning and proof. So I've decided to split up this whole entire topic into two sections, one being geometric reasoning and one being geometric proof. Geometric proof will be the next video coming after this. And what geometric reasoning is, it's actually not necessarily an opposite of geometric proof, but it's completely different. In geometry, proof is what is used to back up or give validity to any step that you take. That can be a concept, a relationship, an equation, or even a simple subtraction sign that's added into your process. So you have to have a proof, and you have to prove it through certain postulates, theorems, and different conjugations as well. So I'll get into that into a later video, but for now we're going to be focusing on geometric reasoning, and geometric reasoning is much different than reasoning in real life. So in real life, an example would be if you're playing in a soccer game and you shot the ball into your opponent's net, you scored in the opposing net. So you have to have a reasoning for that in real life, and the reasoning for that would be you wanted to one-up the other team. Either you wanted to minimize your loss, you wanted to either tie the game or even win the game. So those are the three possible outcomes. Geometric reasoning doesn't necessarily focus on the proof part of completing or accomplishing something or even doing something, but it takes what's already done. It takes the proven that can be either proven true or false, and what you're doing is you're taking that information and you're making a conclusion out of that. So basically you're developing a hypothesis and then you're making a conclusion based off of what you're given in order to help with further situations. So say, for example, if you're in a soccer game and a person scored a goal in the opposing team's net, well, what you can say is, since you know that they're trying to score to win against the other team, you can use your geometric reasoning skills to make a hypothesis and then the conclusion that says if someone scores in the opposing net, then they score an entire a goal or a new point in a soccer game, and they're trying to win against the other team, and that's true for every single situation. So you're taking the specific and then you're applying it to the broad and general that is alike to that situation. All right, let's get into the important parts of reasoning before we get into actually developing reasoning statements. So reasoning is conveyed in the form of statements, which can be proven true or false based on the situation that's presented to you. And statements are created based off of visualization, absorption, and observation, and then you create an assumption about that. That's what a hypothesis is also about. So reasoning itself isn't necessarily an organic form, but reasoning always comes in the form of a statement. A statement is a regular sentence. You're trying to make a point, and it starts with the form of if and then, and I'll explain that later. So yes, reasoning always comes in the form of statements. And here we're going to discover the parts of a reasoning statement. So the first part is the hypothesis. I'm sure you have learned about this in science because it's very important during experimentation. Your hypothesis is basically the absorption and observation of what you're given, and it's basically saying it basically identifies a specific scenario, and you're saying if this were to happen, that's basically your hypothesis. So if something were to happen, would be equivalent to your hypothesis. And hypothesis, as I just said here, are the part of a conditional statement. A conditional statement is a reasoning statement. That's a fancy word for reasoning. And it includes the words if and comes before the then part of the conditional statement. And it's completely observational. And that's important to see here because it's all about analyzation, and that analyzation actually leads you to your conclusion, which is next. And conclusion is basically your final statement or your final conclusion. You're concluding what you're saying. And so what I mean by the words if and before then, this is the form in which a organic reasoning statement comes into play, and I will explain that later. But all you need to know is that a hypothesis is what you take in from a certain situation, and then you absorb that process, you absorb it, and then you make assumptions based off of it. And then you have your conclusion part, which is the next part, the last part of the conditional statement, and it's the part of a conditional statement that includes the words after then, and I'll explain that later. And the conclusion is the overall theory or the solution you come to after analyzing. So hypothesis is basically what you're identifying, like I'm identifying this, 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 and this, and then conclusion is saying based off of this, this, and this, I can conclude that this happens. So just like that, it's very simple. And then an example of a reasoning statement would be if a figure is a square, then it is a rectangle. And notice how I didn't capitalize the I in if. That was actually on purpose because I'll explain later, but these two parts, the hypothesis and conclusion, are always interchangeable, meaning that they don't have to have the hypothesis coming before the conclusion in all scenarios. And of course, your yellow is the hypothesis highlighted and the green is the conclusion. So like I said, conclusion comes after the word if and before the word then. So that's if a figure is a square, so that's a hypothesis. And then the conditional statement includes the words after then, so then it is a rectangle. And this is a true conditional statement. If a figure is a square, then it is a rectangle. All right, now we're going to get into the specific and special scenarios. So these are your every type of construction, type of statements, and then different examples for them. All right, so let's start off with our basic organic statement, which is the conditional statement. It's a statement in the form of which P, then in which it's the statement in the form of P, then in which the hypothesis P implies the conclusion Q. So basically, what it's saying here is that if you look back here, this is a good example of a conditional statement. It's saying that if P being the hypothesis, so if a figure is a square, that's basically stating the hypothesis, a basic scenario, then it is a rectangle. So what it does is it's taking the hypothesis and basically saying that the hypothesis implies a conclusion. So it's saying that if it is a square, then it must be a rectangle. So the conclusion is the independent variable. The conclusion is the dependent variable, and the hypothesis is the dependent variable. Switch that around. Yeah, the I apologize for that. The conclusion is the dependent variable, and the hypothesis is the independent variable. And that's just to go and say that, it's almost like an equation with, y equals mx plus b or y equals x. X in any scenario is always your independent variable, while y is always dependent on x. And in this situation, the conclusion is always dependent on the hypothesis. And this is the organic reasoning statement that's altered in all other scenarios that will be represented here. And the conditional statement is only true when all possibilities are true. So, and it can be disproven with just one counterexample. So I'm going to show you this example here. This is a set of parallel lines, and I'm going to make a conditional statement. So when you're looking at parallel lines, the only way that they're parallel is if they have the same exact slope. So what I can say is, if two lines on a coordinate graph have the same exact equivalent slope or congruent slopes, meaning that they're equivalent, then they are parallel lines. And that is true for every single situation. But if I were to find a single moment or single point or a single situation in which it's not true, then this entire conditional statement is inaccurate. And it has to be true for all reasons, all purposes, and it cannot just be selective purposes. And then this is our part 2 of specific and special scenarios. So another type of reasoning statement that you have is a converse. So just keep that in mind. You have your conditional statement first. And then this is our next statement, which is our converse statement. And it's a conditional statement that switches the hypothesis and the conclusion of the original statement. And it's basically saying when Q, then P. So basically what it's doing is, just as the definition states, the hypothesis is coming after the conclusion. So the when part comes before the then part. So if I were to go back, or I'll just use this example here. So if you're using this example here, it basically has to do with an umbrella in rain. So what I could say is, when it rains, then I have an umbrella. So that can be proven true or that can be proven false, but it depends on the scenario. However, but in generality, this is still true. A converse can be proven to be true, but a converse statement of a true conditional statement, or like a true statement like stated here, if a figure is a square, then it is a rectangle. If you use the converse of this organic conditional statement, it's not going to be true. So it's not necessarily always true if you converse a conditional statement. Because if you look here, if it says a figure is a square, then it is a rectangle. That is always true. However, if it is a rectangle, if you were to say when a figure is a rectangle, then it is a square. That's not necessarily true all the time, because it can be a something other than a square, because it might not have all equivalent sides. So just like that, converse is not necessarily always true. However, when you come to a negation, it is always true. So it's basically saying that when a statement is represented by P, then not P is the negation of the statement. So basically what that means is that if something is not something else. So if you were to say, if a figure is not a square, then it is a rectangle. It's a very non-formal way of conveying a conditional statement, but it is accurate, though. It's always accurate. It's just the opposing of one. And as you may know, a double negative, right here, a double negative always equals a positive. So that's the same thing here. A not, those are double negatives that equal a positive. So if it's not raining, I have my umbrella. All right, now into our part 3 of specific and special scenarios. We have our fourth type of conditional statement, and that's a conditional statement that negates both the hypothesis and the conclusion of the original conditional statement. And this is also the same property that the negation has, because it's basically imposing the double negative principle, which equals a positive, and it's also known as an inverse similar, though. So what you're doing is you're basically negating both the hypothesis and the conclusion. What I'm going to do here is I'm going to make a true conditional statement, and we're going to assume that it's always true. All right. So we're going to assume that it's always true that if I'm going shopping, then I'm going to have a shopping cart. That's my conditional statement. What I can do in order to represent the inverse of that conditional statement, I can basically negate both the hypothesis and the conclusion. So I can say, if I'm not going shopping, then I don't have a shopping cart. That is true as well to the situation. So the inverse is also always true. And then you have the contrapositive, which is our fifth type of reasoning statement, and it's a conditional statement that switches and negates the hypothesis and the conclusion of the conditional statement. So what basically you're doing is you're depending on the original statement, and this flip can either be true or false. So unlike the inverse, this can always change. Because remember, we learned about the inverse, in which you switch the hypothesis and the conclusion. If the original conditional statement, being the hypothesis then the conclusion, is true, it might not always be true with the conclusion then the hypothesis. So I'll give you an example here with the shopping cart. And basically what we're doing is we're negating both the hypothesis and the conclusion, and we're also switching them. So if I were to say, if I'm not going shopping, then I don't have a shopping cart. If you're saying that if you were to switch those and saying, when I don't have a shopping cart, I am not going shopping. That's not necessarily true, because it's not 100% accurate to what I said before. It's not 100% validity to the statement that was said before, but it can be true in certain general situations when two factors are both not necessarily dependent, but they have to be independent. And on to our last part, our part 4, we have our last type of reasoning statement, which is our biconditional statement. And it's a true statement that uses the phrase if and only if, and whose converse is also true. So this is simply when a conditional statement and its converse are both true. That's why it's biconditional. And if I were to say, if and only if it is snowing, then I have a shovel. Then I take out my shovel. That should also be true when you're saying, when I take out my shovel, it must only be snowing. So that's the only reason why. And it has to be true in that biconditional statement. Now, these general statements cannot necessarily be true without numbers or values to represent them, because these are basically real life examples, are very general forms, and unlike geometric examples, they're not very specific. So that's why it has to be dependent on the specific situation of that general statement. And it's also important to find a counterexample of a converse in order to determine whether or not a conditional statement is biconditional, because the only thing that makes a biconditional statement is a conditional statement with this a converse that is also true. So that's very important to figure out. All right, guys, so that'll be it for today's geometry lesson on geometric reasoning. It's been AJay Raj through our eCoreAcademy e-learning platform. Please make sure to like and subscribe, as I'm reiterating at the beginning of the video, and also hit that bell to get notified on any of our latest posts. Visit our website at eCoreAcademy.org. All of our socials listed here at Facebook, Twitter, Instagram, and Google Space, as well as emailing us at Gmail if you have any questions or you just want to talk to us at eCoreAcademy@gmail.com. All right, guys, it's been AJay Raj here, and I'll see you in the next one. Peace.